Throughout human history, war technology has been the most decisive factor in the rise and fall of societies. Early humans struggled to survive with simple stone tools, but soon began using these tools not only for hunting, but also in their battles against rival tribes. Stone spears, primitive arrows, and axes were the most important weapons of early warfare. Over time, bronze and iron began to be processed. Swords, spearheads, and armor made of bronze determined the fate of the side that gained superiority on the battlefield. History shows us this. Whoever had better technology most often won the war. The invention of gunpowder radically changed the course of wars. Originating in China, gunpowder soon led to the development of cannons and firearms. This meant that castles and fortresses in the Middle Ages no longer provided sufficient defense. Suddenly, the feudal system began to collapse because massive stone castles were helpless against cannons. With the spread of firearms, the doors of the modern age were opened. Then came the Industrial Revolution, which transformed not only the economy but also the very nature of war. Steamships, armies transported by railroads, armored warships, tanks, and aircraft entered the stage. By the 20th century, humanity was confronted with its most terrifying invention, the nuclear bomb. In 1945, the bombs dropped on Hiroshima and Nagasaki wiped out hundreds of thousands of people within seconds and opened a new chapter in the history of war. Today, however, we are in a completely different era. Wars are no longer fought only with tanks, rifles, and cannons. They now unfold on invisible fronts, in computer networks, under the shadow of satellites, and under the control of machines operating without human touch. Among modern war technologies, one of the most prominent is hypersonic missiles. These weapons, with their speed, maneuverability, and ability to render defense systems completely ineffective, are considered one of the most critical technologies of today and the future. When one hears the term hypersonic missile, the first thing that comes to mind is their incredible speed. The speed of sound, Mach 1, corresponds to about 343 meters per second at sea level, or 1,225 kilometers per hour. Today, most fighter jets can reach Mach 2 or Mach 3. However, hypersonic missiles travel above Mach 5, which is at least 5 times the speed of sound. This means speeds above 6,000 kilometers per hour. In some tests, speeds of Mach 10, about 12,000 kilometers per hour, have been reported. A weapon traveling at such speed could cross intercontinental distances within minutes. But what makes hypersonic missiles dangerous is not only their speed. Their real difference lies in their ability to maneuver. Traditional ballistic missiles follow a fixed ballistic trajectory once launched, making their landing point relatively predictable. Defense systems try to intercept by calculating this trajectory. In contrast, hypersonic missiles can maneuver within the atmosphere. They can change direction while heading toward the target, disrupting the defense system's calculations. Even if radars detect them, predicting where they will go becomes nearly impossible. At this point, we must delve a little into the depths of science. A body traveling at hypersonic speeds experiences such intense friction with the atmosphere that a plasma sheath forms around it. Plasma is ionized gas, meaning that molecules in the air lose their electrons due to extreme heat and pressure, turning into ions. This plasma sheath makes the missile virtually invisible because radar signals bounce off it, making it very difficult to determine the missile's exact location. Moreover, this plasma generates temperatures of thousands of degrees on the missile's surface. Therefore, the bodies of hypersonic missiles must be made of special heat-resistant materials. Ceramic composites, carbon-based materials, and ablative coatings are used for this purpose. Ablation means controlled burning or vaporization of the surface to dissipate heat. In other words, the outer surface burns away, but the interior remains protected. There are 2 main types of hypersonic missiles: hypersonic cruise missiles and hypersonic glide vehicles. Cruise missiles are generally powered by scramjet engines. Scramjet, or supersonic combustion ramjet, is a type of engine where combustion occurs at supersonic speeds. In normal jet engines, air is compressed, mixed with fuel, and burned. In scramjet engines, however, combustion takes place while the airflow remains supersonic, allowing the engine to keep operating even at hypersonic speeds. Thanks to scramjets, missiles can reach incredible speeds within the atmosphere. Hypersonic glide vehicles, on the other hand, operate differently. They are usually carried to high altitudes by a rocket, and then glide back into the atmosphere like a glider. During this phase, they can maneuver and confuse defense systems. Russia's Avangard system and China's DFZF are examples of such glide vehicles. Avangard is claimed to reach speeds up to Mach 20, that is, 25,000 kilometers per hour. This means it could strike any point on Earth in less than half an hour. One of the biggest problems caused by hypersonic missiles is that current defense systems are not prepared to counter these speeds. Systems like Patriot, THAAD, or S-400 are designed to intercept ballistic missiles or aircraft at certain speeds. But a hypersonic missile is both much faster and capable of altering its trajectory. Therefore, today, no country is fully secure against hypersonic attacks. The United States is working on a new system called the Glide Phase Interceptor, which aims to stop hypersonic missiles during their glide phase within the atmosphere. However, these technologies are still under development. Here's another interesting point. Hypersonic missiles do not have to carry nuclear warheads. They can also be armed with conventional explosives. Yet, because of their speed, even a non-nuclear warhead can cause massive destruction. That's because kinetic energy, energy of motion, increases with the square of speed. A few-ton mass traveling at Mach 10 would strike with immense energy. Though not as destructive as a nuclear blast, it could still cause catastrophic damage. The strategic implications of hypersonic missiles are enormous. These weapons could weaken the traditional nuclear deterrence system. If a country possesses hypersonic weapons, the likelihood of striking its rivals before they can retaliate with nuclear weapons increases. This upsets the balance of power. For this reason, hypersonic missiles are seen not only as military tools, but also as political weapons today. With all these features, hypersonic missiles have become one of the most critical elements of future wars. The world's major powers are spending billions of dollars to develop this technology. Whoever gains superiority in this field will also have the advantage in future wars. And this brings us to a fundamental question. Where is humanity headed with weapons like hypersonic missiles that are nearly impossible to defend against? Is the rapid development of war technology driving us toward peace or toward greater catastrophes? Although hypersonic missiles are among today's most talked about weapons, humanity's greatest nightmare remains nuclear weapons. To understand the power of these weapons, one must look at both physics and history. At the heart of a nuclear weapon lies the immense energy stored within the atomic nucleus. In normal chemical explosions, energy comes from the breaking and reforming of bonds in the electron arrangements of atoms. Molecules separate and recombine in different configurations, releasing relatively small amounts of energy compared to the power hidden inside the atomic nucleus. In nuclear weapons, however, the secret lies in the nucleus itself. The first nuclear weapons were fission bombs. Fission, or splitting, is the process where heavy atomic nuclei break into smaller parts. Isotopes like uranium-235 or plutonium-239 are suitable for this reaction. When a neutron collides with such a nucleus, it splits into two, releasing more neutrons. These neutrons then split other nuclei, creating a chain reaction. If enough fissile material is gathered, the chain reaction happens almost instantaneously, releasing enormous energy. The bombs dropped on Hiroshima, Little Boy, and Nagasaki, Fat Man, worked on this principle. But fission bombs were only the first step in harnessing nuclear energy. Humanity later developed the fusion bomb. Fusion, or joining, is the process where light atomic nuclei combine to form heavier ones. This is also the energy source of the Sun. Hydrogen nuclei fuse into helium, releasing tremendous energy. However, fusion requires extremely high temperatures and pressures to begin. That's why hydrogen bombs use a fission explosion first to create the conditions necessary for fusion. This results in a far more powerful explosion. Thermonuclear, or hydrogen bombs, can be thousands of times stronger than the bomb dropped on Hiroshima. The largest nuclear explosion in history occurred in 1961, when the Soviet Union tested the Tsar Bomba. This bomb had a yield of about 50 megatons, 3,000 times more powerful than the bomb dropped on Hiroshima. The mushroom cloud reached 60 kilometers high, and seismic instruments worldwide recorded the blast. Such a weapon could wipe not just a city, but an entire region off the map. The true destructive power of nuclear weapons lies not only in the explosion itself, but also in radiation. The neutrons and gamma rays released in fission and fusion reactions destroy living tissues. Furthermore, radioactive fallout, the particles dispersed into the atmosphere after the explosion, renders environments uninhabitable for decades. That's why a nuclear war would affect not just its immediate targets, but the entire world. The deterrent power of nuclear weapons comes from this. During the Cold War, the United States and the Soviet Union adopted the doctrine of mutually assured destruction. This meant that if one side attacked, the other would retaliate, and both would be annihilated. This terrifying balance prevented nuclear weapons from being used, but also kept the world under constant threat. Even today, these weapons remain the strongest hidden card on the table of international relations. The methods of delivering nuclear weapons also sparked a technological arms race. Land-based intercontinental ballistic missiles, ICBMs, submarine-launched missiles, and strategic bombers make up a nation's nuclear triad. This triad guarantees a country's second strike capability, the ability to retaliate even after being attacked. Nuclear submarines, in particular, lurking deep in the oceans, form an invisible threat. Yet, another technology has grown in the shadow of nuclear weapons: fighter aircraft. In modern warfare, high-speed, maneuverable, and stealthy aircraft dominate the skies. Looking back, the history of fighter aircraft began in World War I with reconnaissance missions, but quickly turned to combat. In World War II, the introduction of jet engines dramatically increased speed and altitude capacity. One of the war-changing aircraft was the German Messerschmitt Me-262, the world's first operational jet fighter, which outperformed piston-engine planes of its time. During the Cold War, the United States and the Soviet Union entered a race for speed, culminating in the SR-71 Blackbird. Developed by Lockheed, this aircraft could fly over Mach 3, more than 3,500 kilometers per hour. It was so fast that no missile could catch it. Its body was made of titanium alloys, since ordinary aluminum would melt at such speeds. The most critical feature of modern fighter aircraft, however, is stealth technology. Radar waves reflect off metallic surfaces and are detected by ground stations. Stealth aircraft minimize this reflection thanks to special geometries and radar-absorbing coatings. The F-117 Nighthawk, the B-2 Spirit bomber, and today's F-22 Raptor and F-35 Lightning II are the best-known examples of this technology. These planes can infiltrate enemy airspace undetected and strike their targets. Aircraft engines are also marvels of engineering. Modern jet engines have turbine blades that can withstand thousands of degrees of heat. These blades are often made of nickel-based superalloys and protected with ceramic coatings. In addition, afterburner systems inject fuel directly into the exhaust, dramatically increasing thrust for supersonic flight. Of course, modern warfare is shaped not only by aircraft, but also by missiles. Ballistic missiles rise into the atmosphere using rocket engines, then fall toward their targets by gravity. They can reach very long ranges. Cruise missiles, by contrast, fly within the atmosphere, usually powered by turbojet or turbofan engines, and approach targets at low altitude to evade defenses. The Tomahawk cruise missile is one of the most famous examples. Defense systems are constantly evolving to intercept these missiles. The Patriot system is one of the best-known US air defense systems. The Soviet-developed S-300 and more modern S-400 systems stand out for their ability to strike aircraft and missiles at high altitudes. The US THAAD system aims to intercept ballistic missiles outside the atmosphere. Israel's Iron Dome system protects cities from short-range rockets. Yet despite all these systems, defenses remain insufficient against new threats like hypersonic missiles. This is why war technology is in a constant race. As offensive technologies advance, so must defensive technologies. This endless cycle is the harshest reality of human history. Nuclear weapons, fighter jets, and modern missiles are the most strategic components of today's armies. The science behind them involves not only engineering, but also physics, materials science, aerodynamics, thermodynamics, and computer technology. Thus, war technologies are actually a reflection of humanity's scientific capacity. But will this capacity be used for peace or for destruction? That is the question that will determine our future. One of the greatest revolutions in modern warfare has been unmanned aerial vehicles, or drones. Initially used only for reconnaissance and surveillance, these machines have become one of the most important elements on the battlefield. The rise of drones has fundamentally changed the nature of warfare. While a fighter jet costs millions of dollars, a drone is much cheaper. More importantly, there is no risk to a pilot's life. Human casualties are avoided because drones are remotely controlled or operate autonomously. These features have made drones decisive in recent conflicts. Turkey's Bayraktar TB2 provided Azerbaijan with a major advantage in the Nagorno-Karabakh war. The US's MQ-9 Reaper drones have been widely used in Middle Eastern operations. Israel's Heron drones have been active in the region for years. The true power of drones emerges when combined with artificial intelligence. Thanks to image processing algorithms, drones can independently detect targets. Object recognition systems can distinguish a tank, an aircraft, or a military convoy from other objects. These systems work like the human eye, but much faster. Camera feeds are processed by neural networks trained on millions of examples. Thus, a drone can determine within seconds whether what it sees is a target. Swarm drone technology could transform future wars completely. Hundreds or even thousands of small drones could take off simultaneously, coordinating with AI support. These drones communicate with each other, share tasks, and collectively attack targets. Stopping such a swarm would be nearly impossible for traditional defenses, since defense systems can only strike a limited number of targets at once. But when hundreds of drones attack in waves, defenses are quickly overwhelmed. This technology could make the concept of unmanned armies a reality. AI's role in warfare is not limited to drones. Artificial intelligence is beginning to enter the very decision-making mechanisms of war. Imagine a military command center. Intelligence reports, satellite images, radar signals, and battlefield updates all arrive at once. All this data must be processed simultaneously. The human brain cannot analyze so much data so quickly. This is where AI steps in. Big data algorithms can scan millions of data points in seconds, calculate probabilities, and recommend the best strategy. However, the critical role of AI in warfare raises major ethical debates. Should the decision to kill in war be made by a machine? Can an algorithm decide which target to strike or which attack to launch? Ethically, this is highly dangerous. Algorithms can make mistakes. A school bus might be mistaken for a military vehicle and attacked. This is why the rise of AI in the military is not just a technological issue, but also a moral and philosophical one. Meanwhile, another invisible but increasingly dangerous front is cyberspace. Modern societies are completely dependent on digital networks. Power grids, communication systems, banks, water supplies, even hospitals, everything is run by computer networks. At this point, cyber attacks can paralyze a country without firing a single bullet. In 2010, a computer virus called Stuxnet attacked Iran's nuclear program. This virus infected the centrifuges at the Natanz uranium enrichment facility. While making them appear to function normally, it actually altered their speeds and caused them to break down. This event became the first digital sabotage in history. Cyber attacks have since become a new way to harm rival states without physical warfare. In 2015, a cyber attack in Ukraine left millions of people without electricity. A few lines of code written by hackers were enough to collapse the infrastructure of an entire country. These events show us this. The wars of the future may be fought through computer screens. It may become possible to disable a country not by bombing its cities, but simply by pulling the plug. Methods used in cyber warfare include viruses, trojans, ransomware, phishing attacks, and distributed denial of service (DDoS) attacks. Cryptography lies at the heart of this battle. A state capable of breaking encryption systems could read all of its rivals' secret communications. The entry of quantum computers into this field poses a huge risk, since codes that would take classical computers thousands of years to break could be solved in seconds with quantum computing. In addition to cyber warfare, electronic warfare is one of the most important tools of modern armies. Jamming radar signals, disrupting GPS, and blocking enemy communications are invisible but deadly methods of combat. Electronic warfare operates across the electromagnetic spectrum: radio waves, microwaves, infrared, visible light, and beyond. A radar sends electromagnetic waves and collects the reflections. If an enemy jams these signals, the radar sees nothing. GPS signals come from satellites. If the enemy disrupts them, targeting systems fail. Electronic warfare can neutralize even a country's most advanced weapons. Finally, let us mention energy weapons, once confined to science fiction but now becoming reality. High-powered lasers are being tested in many countries today. These lasers can destroy a drone or missile in seconds while in flight. Their greatest advantage is their speed. They travel at the speed of light, meaning their time to reach the target is nearly zero. They also have no ammunition limit. As long as there is a sufficient power source, they can fire endlessly. Microwave weapons work differently. High-energy microwaves disable electronic systems. A tank's or aircraft's circuits could be burned out by a powerful microwave burst, rendering them useless. The US, China, and Russia are all working on such weapons. There is even talk of developing particle beam weapons in the future. High-energy particle streams could cause major damage upon impact. Though still experimental, scientists are researching this area. The spread of energy weapons could fundamentally alter warfare. Drones, missiles, and aircraft could be instantly destroyed by lasers, taking wars to an entirely different level. Drones, AI, cyber attacks, electronic warfare, and energy weapons. Together they create a picture that is both dark and fascinating. War is no longer fought solely on the battlefield with tanks and rifles, but also on invisible fronts, in the hands of machines and algorithms. And as these technologies evolve, humanity faces an even greater question. Will future wars be won by humans or by machines? Humanity has shaped war technology not only with massive strategic weapons, but also with small yet effective tools used on the battlefield. One of the most famous is the AK-47. Designed by Mikhail Kalashnikov, this assault rifle became the world's most widespread weapon thanks to its simplicity, durability, and low cost. It still works after being dropped in mud or neglected without maintenance. It is estimated that there are more than 100 million AK-47s and their variants worldwide today. The symbol of the US Army is the M16 rifle. When first used in the Vietnam War, it faced many problems, but over the years it was improved and became the standard rifle of modern armies. Later, the M4 carbine became the new standard for American soldiers. These weapons show that ergonomics and ease of use are just as critical as technological superiority on the battlefield. In modern wars, anti-tank systems have also become vital. The Javelin missile, a shoulder-fired guided anti-tank missile, operates on the fire-and-forget principle. Once the soldier fires, the missile tracks the target on its own. This capability enabled many tanks to be destroyed by Javelin missiles in the Russia-Ukraine war. The Stinger missile is one of the best-known portable air defense systems. Fired from the shoulder and infrared guided, Stingers allowed Afghan Mujahideen in the 1980s to shoot down Soviet helicopters, changing the course of the war. Looking to the skies, we also see iconic warplanes throughout history. The legendary Spitfire of World War II was Britain's greatest hope against Nazi aircraft in the Battle of Britain. The Soviet MiG series, particularly MiG-21 and MiG-29, symbolized Soviet power during the Cold War. In modern times, the F-22 Raptor and F-35 Lightning II stand out with stealth technology. The F-22 is considered the world's first fifth-generation fighter, with super maneuverability, radar invisibility, and speeds above Mach 2, earning it the title of ruler of the skies. The F-35 is a versatile aircraft capable of both air-to-air and air-to-ground missions, also excelling in electronic warfare. But perhaps the most special aircraft in history is the SR-71 Blackbird. It was so fast that no missile could catch it, flying above Mach 3, over 3,500 kilometers per hour. Its body was made of titanium alloys, as ordinary metals would melt at such speeds. Used for reconnaissance during the Cold War, the Blackbird was never shot down. Among bombers, the B-2 Spirit is iconic. Thanks to stealth capabilities, it can infiltrate enemy airspace undetected. Although expensive and produced in small numbers, it remains a symbol of modern warfare. Tanks are indispensable on the battlefield. In World War II, the German Tiger I tank terrified enemies with its thick armor and powerful gun. The Soviet T-34, however, with its simplicity, durability, and numbers, changed the course of the war. In the modern era, the American M1 Abrams stands out with thermal sights, composite armor, and a gas turbine engine. Europe's pride, the Leopard II, excels in mobility and firepower. Russia's T-14 Armata, with its unmanned turret and automatic loader, heralds the new generation of tanks. Missiles and defense systems are also critical in modern warfare. The American Patriot system became a symbol of air defense for years, capable of destroying ballistic missiles and aircraft at certain altitudes. Russia's S-400 system stands out with its long range, ability to strike high-speed targets, and capacity to lock on to multiple targets at once. China has also joined the race by developing its own systems. Israel's Iron Dome system has proven highly effective at protecting cities from short-range rockets, detecting incoming rockets and destroying them in mid-air. Among offensive missiles, the Tomahawk cruise missile is one of the best known. It flies at low altitude, slipping under radar coverage, and strikes with precision. Russia's Kalibr missiles offer similar long-range precision strikes. These weapons have become among the most frequently used tools of modern militaries. All these iconic weapons, aircraft, tanks, and missiles show that war technology is not just a mechanical race, but also a scientific one. Aerodynamics, ballistics, materials science, electronics, artificial intelligence, all are part of this race. But the future of war technology is moving toward a very different arena. Space could become the next battlefield. Many countries are already working to protect their satellites and to disable enemy satellites. Destroying a nation's communication satellites would paralyze its military. For this reason, research is underway on space-based lasers, satellite-killing systems, and even orbital weapon platforms. Quantum technology could also change the future of warfare. Quantum computers could break encryption systems in seconds. Quantum radars could detect stealth aircraft. Quantum communication systems could provide unbreakable encryption. Artificial intelligence could completely transform military decision-making. Perhaps in the future, humans will only be observers in wars, while algorithms make the decisions. Drone swarms, autonomous tanks, unmanned submarines, and AI commanders may shape the course of future battles. But looming over all these technologies is the same question. Can humanity control its own inventions? Or will these inventions prepare the path to humanity's own destruction? History has shown us this. When war technologies were developed, they were eventually used. From stone axes to nuclear bombs, everything has appeared on the battlefield. So will hypersonic missiles, energy weapons, AI armies, and space weapons also be used. If they are, it could be humanity's last war. Perhaps future wars will not be won by humans, but by machines. But after those wars, will there be a world left to live on? That question is humanity's responsibility, not only for scientists and engineers, but for everyone. War technologies demonstrate how much humanity has mastered science. But they also show how humanity has chosen to use it. Will we use this science for peace or for our own destruction? The answer to this question will determine the fate of the next century. And perhaps for the first time in history, war technologies have become powerful enough not only to lead us to the next war, but also to the very end of humanity itself.